All right, here we go. You'll notice this is 8.2. Actually skipped section 8.1 and we jump right into 8.2 for chapter 8. In this lesson, we're going to learn a little bit about what are called the reciprocal function family, or the reciprocal functions. Hopefully the word reciprocal is familiar to you, being just a fraction that's been flipped. We'll get into a little bit more about it, but just to kind of get the idea of a real world scenario for a reciprocal function. So imagine we're going to throw a pizza party. Okay, order a bunch of pizzas. It's $150. I throw out there, hey, you all going to chip in some money? Everybody says yes. There's 30 of us in the class. Not bad. And then come pizza time, no one pays. It's just me that has to fork out the bill for all the pizza. So if there's only one person paying for that pizza, how much is the cost per person? Well, if I have to front the entire bill, obviously my cost is going to be $150. Now let's say one other student says, you know what, Mr. Lucan, I'll help you out. I'll take care of it. Maybe you just want a $50 gift card. Maybe your name's Haley. Maybe you want to help pay for this pizza. So now we're up to two pairs. Okay. What does that do to the overall cost per person? Well, now Haley and I are splitting it, so this goes down to $75 each. Okay. A couple more people raise their hands. They say, you know what? It's fine. I get it. I like pizza. I'll chip in. We get 5 people paying. What's that going to do to the cost? It is going to keep decreasing per person. So if I take now $150 and split it amongst 5 people, now each person's paying $30. We could keep going with this, right? I could say, oh, what if there's 10 people paying? Well, now it's $15 each. There's 15 people that are going to pay 150 divided by 15. Now each person only has to pay 10. And let's say the entire class shows up, wants to help out. Bam. Now for 30 people, it's only $5 each. Okay. So this idea where one value getting larger, in this case, the number of people paying, leads to a smaller cost per person. This is what's going to lead to something called a reciprocal function. Okay. One value, in this case, the x value getting larger, leading to the y value getting smaller. And then 2 questions that are really important. How much will it cost per person if no one is willing to pay? If there are 0 people paying, how much will it cost each person? Well, that'd be like saying I'm going to take $150 and split it amongst 0 people. Not possible. Okay? It doesn't make sense to say how much does each person pay if no one's paying. So this doesn't exist. This is impossible. Okay? That doesn't really even compute. And the flip side of that, how many people would we need to go in on this pizza for the cost per person to be 0? Like, everybody in the world is going to pay. We're all going to split evenly. So it costs $0 per person. Like, truly 0. And that's also not possible, right? Because no matter what, somehow we're going to have to make $150. So even if it's a very, very small amount of money, you can never get the cost per person to be exactly 0. Okay. And we're going to see how this works out mathematically right now. So maybe we'll have this happen, but if we're going to have a pizza party, I do need people willing to pay. So a reciprocal function is simply defined as a number divided by x. Okay. So in order to be a reciprocal function, it has to be any number, any whole number. I guess it could be a decimal too, divided by x. Okay. So for example, here's one possibility: y equals 2 divided by x. Now to build this, I'm just going to pick some random numbers to kind of get what the graph of what this looks like. I'm going to pick a couple positive and a couple negative x values and plug them in. One thing that I'm not going to be able to do, normally when we graph, we go from -2 to +2. Oops. From -2 to +2. There's obviously an issue with this, and that is that I can't plug in 0. Right? This number is not going to work because I can't do 2 divided by 0. So what I'm going to do is I'm going to pick 2 negative numbers. I'm going to skip over 0 and then pick 2 convenient positive numbers. So if I do 2 divided by -2, that gives me -1. 2 divided by -1 gives me -2. 2 over 1 and 2 over 2. Okay, so you see how they kind of like switch spots, right? If x is -2, then y is -1, and then in the next row they reverse spots. So I'm going to graph those points. Okay, -2, -1. So -2, comma -1. Oops. And -1, comma -2. Now, and then if I graph the positive versions, 1, oh, not 1, 1. It was 1, comma 2, and 2, comma 1. Now this is a pretty odd set of points to try and connect in a graph. But what's also important is that you understand that 0 is not possible, right? I can't plug in 0 for x, which means I'm going to have a vertical asymptote at x equals 0, meaning I cannot cross the y-axis at all. I'm going to approach the y-axis, but I'll never truly get there. And by that same token, if I were to do 2 divided by 3, 2 divided by 4, 2 divided by 5, this number would get smaller and smaller and would approach 0, but it would never truly get to 0. So to see what this graph looks like, we're actually going to use Desmos here real quick. Okay, we're going to look at these graphs later on. We're going to take a look at y equals 2 divided by x. So if you see, here are the points that we graphed, right? There's 1, comma 2 right there, and there's 2, comma 1. But we have sort of a double asymptote thing going on. So there's both a vertical asymptote as well as a horizontal asymptote. So I can't divide by 0, but I can never quite get to 0. So this graph is going to be a new one. It's going to look something like this, where I'm going along the asymptote in both directions. Okay, this is going to look something like that. So I've got both. This is the first function that we've seen that has both a horizontal and a vertical asymptote. Okay, the horizontal asymptote would be y equals 0. And then we can fill out the domain and range for this. The domain, what values of x can I plug into this function? I can divide 2 by any number except for 0. So I'm just going to say x cannot be 0. Anything else is fair game. And for y values, I also can't get 0 out. I can get very close to 0 by taking 2 divided by a big number, but I'll never get to 0. So you'll notice the domain and the vertical asymptote go together, and the range and the horizontal asymptote go together. What happens then if I put a negative number up in the numerator? So if I do -3 over x, let's pick convenient numbers that can avoid decimals. So I'm going to go ahead and divide by -3 and -1 for the negative x values, and then +1 and +3. If I plug each one of these in, you see what happens here. If -3 divided by 1, -3 divided by 3. Okay. Whereas in the first table of values, I had negatives with negatives and positives with positives. Now they intermix. So I've got a negative number with a positive y value. So if I plot these points, -3, comma 1, -1, comma 3, 1, 2, 3. Okay, 1, comma -3, and 3, comma -1. Again, you can maybe guess what this is going to do. If I replace that 2 with -3, you'll see that still that same sort of shape, but now it is switched to the other quadrants of the graph. Okay, this is quadrant 1 is in the upper right, quadrant 2, quadrant 3 in the lower left, and quadrant 4. So what I'm going to do is just graph these here. Oh boy, that wasn't great. Okay, still has the same asymptotes. So what's crazy about this is these two functions look different, are in different quadrants. So I'm going to put, for here, this was quadrants 2 and 4. And then over here, we were in quadrants 1 and 3. Okay, And that is completely dictated by whether it's a positive or a negative number on top. What's interesting though, and we're going to highlight on the next slide, is this is true for everything. Every reciprocal function, if you replace the 2 or the -3 with any number, that's going to be your domain and range, which is nice because domain and range can be difficult to determine sometimes, but these are the exact same always. All that matters is which quadrants we're in. Okay, so again, kind of looking here, this is what your graph is going to look like if your a value is greater than 0. So if the numerator is a positive number, then you're going to be in quadrants 1 and 3. These are called branches, by the way. Okay, so this is one branch and that's the other branch. We're not talking legislative and presidential. I don't think it's called presidential. Anyway, and if the a value is less than 0, we have branches in quadrants 2 and 4. Okay, but again, all of these reciprocal parent functions, now we are going to translate a little bit later, but they all have the same domain where x can't be 0, which leads to a vertical asymptote at 0. The range can't equal, y can't be 0 because I can't take a number divided by something and get 0, which leads to a horizontal asymptote at 0. This is what's kind of interesting. If you plug in 1 for the x value, so take any number divided by 1, and you'll get that same number back, so 1 comma a. And then, again, if you take any number and divide by itself, so if I were to plug in, let's say a here, if I were to replace this with a, and I have a divided by a, that would give me 1 every time, no matter what the number is. So we're going to use this fact here to make graphing a lot easier in a little bit. Okay, so all of these reciprocal functions have these same characteristics. Kind of a long-winded way of saying it, but it's really important because we're going to build off of here. Now what's the translation? Okay, so same thing with logs, same thing with square roots, same thing with parabolas. We're going to first look at the parent function. So when I scan this thing, okay, and you can plug the entire thing in your calculator, but again, like, it's good to know where these things come from. The parent function is simply, I'm going to ignore all the translations. So my parent function that we're going to start with is y equals 1 over x. Okay. So I'm going to just plug in some values here. When x is 1, y is 1. When x is 2, 1 divided by 2, that's 0.5. Same thing with the negatives. If I plug in -1, I get -1, and -2 is -0.5. Okay. Now, while those coordinates are different, I still have the same domain and range. So domain, x can't be 0. For the range, y can't be 0, because those are the asymptotes. Okay. So now if we look here, right, I have that +3 is going to move to the left 3 units, which means for the x values, I'm going to take away 3. And for the -2, that's going to go down 2, which means the y coordinates will subtract 2. Okay, so I can go ahead and take away 3 from all these x values. So +1, this becomes -2, that's -1, -4, and -5. Okay, and then for the y coordinates, I'm going to take away 2 from each of those. So I'm just going to take those and subtract 2. -1, -1.5, -3, and -2.5. But here's what's interesting, is that the domain and range completely switch. Okay, just like with the log functions and the exponential, if you slide a graph side to side or up and down, the asymptotes have to move with it. So here, since I subtracted 3 from all of my x coordinates, the same thing is going to happen to my domain. So instead of being x is not equal to 0, now I'm going to say x can't equal -3. if you think about it, if I were to replace x with -3, this would be bad news because I'd be dividing by 0, which is like one of the few mathematical things we can't do. Okay. So my domain now is x cannot equal -3, which tells me where my asymptote is. So the vertical asymptote is going to be at x equals -3. For the range, it's the same thing. Y couldn't equal 0 before, but now we've shifted everything down 2. So the range is going to be y can't equal -2, and the horizontal asymptote then is going to be at -2. So we've taken those dashed lines that were at 0 and 0, and we've shifted them. Okay, so that's all the characteristics for it, but now we're going to actually graph this thing. Okay, this is the exact same function. Okay, so we already have the coordinates here: -2, -1, -2, -1, and then it was -1, -1.5, I believe. -4, -3, -4, -3, and -5, -2.5. Okay, then we said x can't be -3? X can't be -3 and y can't be -2. Okay. So to sketch this, I'm going to first put my asymptotes in. So I'm going to put a vertical asymptote at -3 on the x-axis. So I'm going to go to -3 on the x-axis and go straight up and down. And then I'm going to go to -2 on the y-axis and go side to side. Okay. So those are my two asymptotes. You'll note that they meet right there in the middle. And now I'm going to graph my points. So -2, -1 is right there. -1, -1.5 is right there. So you can kind of see that branch forming. -4, -3, 3, 4, 1, 2, 3. And -5, -2.5 is right there. Okay. So I get something that's going to look kind of like this. And right now we're just sketching, but that gives us a general graph. And then you could either go to your graphing calculator or to Desmos. What we had 1 over x plus 3. So notice when I do +3, it just shifts everything to the left. And then I had a -2 on the outside, so then that moves everything down. Okay. The downside with the graphing calculators is it doesn't tell you the asymptotes. But if you plug it, Desmos is kind of nice because if you plug in your asymptote equations, you can kind of see those are the spots where the graph is not going to cross. So if I make both of these dotted, okay, we can kind of see there's the graph and how it approaches the asymptotes but never quite gets there. That was a lot. But when we're translating, again, we're going to use the same parent function and go from there. Here's another way to do it, and I think this way is a little bit easier, is I'm going to take, so here's what I'm going to do. Okay, I look at this x minus 4. I know that's going to shift everything to the right 4 units. Okay, well, if the parent function can't equal 0 and I shift everything to the right, that means now my new domain is going to be x can't be 4, which means my vertical asymptote is equal 4. Okay, that's what happens when I move everything to the right. And then for the range, that's going to move everything up 6 units. So now the range, instead of being y can't equal 0, it's going to be y can't equal 6, and that's my horizontal asymptote. Okay, so what I'm going to do here is I'm going to go ahead and put the asymptotes on right away. So I'm going to put the vertical asymptote at 4, and then the horizontal asymptote at positive 6. 1, 2, 3, 4, 5, 6. Okay. Now, to get the coordinates for that, I'm going to just deal with the parent function. So I'm going to keep it simple. I'm just going to go 2 over x and make some xy coordinates for that. So if x is 1, 2 divided by 1. If x is 2, that's 1. And I can do the same thing with the negatives, -2 and -1. Now, here's the other way to do this, okay? Instead of taking those coordinates and translating them and moving them right 4 and up 6, what I'm going to do is I'm going to plot these exact 4 points, okay? And we've actually done this before with the square roots, but I'm going to treat where my asymptotes cross right there. That is going to be 0, 0. Okay, so if I think of that coordinate, that point where the asymptotes cross, if this, I can think of that as 0, 0, then I'm just going to graph these 4 points. So I'm going to graph 1, 2. So from this new origin, 1, 2 would be right there, 2, 1, -1, -2, and -2, -1 would be right there. Okay, so what I've effectively done is I've moved the entire graph without actually having to change the coordinates. So it goes something like that and something like that. Okay. So that's another way to graph it, and kind of my preferred way for me personally. So take the parent function coordinates and then graph them based on the new origin where the asymptotes cross each other. Okay. So we'll do one more backwards now, and this is the last thing that we have to take a look at, is what graph matches, or what equation matches this graph. Okay, so if you want to try and figure it out, go ahead and pause it. But how I'm going to go about doing this is I see the origin 0, 0 is where the asymptotes would cross. If I had a parent function, just a standard 3 over x or 5 over x, now the asymptotes are cross at the coordinate -1, -4, which means this graph was moved to the left 1 and it was moved down 4 units. Okay, so I know in order to move something left 1, I'm going to see x plus 1 in the denominator, and to move something down 4 units, I'm going to see -4 out front. All that's left for me to do is to figure out what number goes up here. Okay. And in order to do that, we're going to go back to an earlier slide. Okay. And we're going to use this fact right here, that the coordinates, that the reciprocal functions have to go through 1, a. And how we're going to use that is I'm going to take a look at the origin. Okay, I'm going to look at where the asymptotes cross right there. If I treat that as 0, 0, if you had me earlier, we did the same thing for parabolas. I'm going to move 1 unit to the right. Okay, and then I'm going to count to get back to the function from here. Do I have to go up or down? And we can see I have to go down 1, down 2, down 3 units to get back to that curve. So since I moved to the right 1 and down 3, that tells me that the a value, or the number on top of this thing, is going to be -3. Okay, and I'm sure we can go through some more examples and explain through that again. But from where the asymptotes cross, you're going to count 1 unit to the right, and then either go up or down. In this case, I had to go down 3 times, so that gave me the a value on top of my function. So this equation, y equals -3 over x plus 1 minus 4, matches the graph that you see there. Okay, a lot of information, a lot of new stuff, and I know this is a little bit longer. Homeworks from 8.2, just a handful of problems practicing these graphing things. But again, you can go into your calculator, right? I could type in y equals, if we take that last example, right, that last equation that I asked you to graph, it was 2 over, I would have to put x minus 4 in parentheses. Okay, that's every calculator. You're going to have to do this. and then plus 6 afterwards. And I can go to the table and get my coordinates. But again, I need to see where those asymptotes are. You got to show, and if you hit graph, you can kind of see that we have the 2 branches of this thing, but it's not super obvious where the asymptotes are at, and that's where we need to use our knowledge of transformations to get something that looks good. So wrap this up. 8.2, video 1 done.